Alright, hello everyone. In today's video, we are going to be going over this problem involving a water bottle being heated. I already have all of the whiteboard stuff explaining all the equations and the math that's going to be going into this problem, and I already have most of the code written out. I spent about 5 hours making this video last night, and I had everything all put into my iMovie, and then I ran out of storage. So I was cleaning out storage and accidentally deleted most of my video files, and I don't think I'm going to have the time to spend another 4 hours remaking that video, so I'm just going to be going over explaining what I've done so far. I have pretty much everything done. I had everything recorded. All I had to do was add the last few lines of code for my equations in, and the video would have been done, but mistakes were made last night, and actually almost came very close to crying. I think a single tear rolled down my cheek. It was very cinematic. Could have won an Oscar for my performance, but yeah, if you want me to remake the video, I can do that. It'll probably be a while though. I'm going to be very busy this next week or so, but I can definitely get that remade eventually. But for right now, just to get the playlist uploaded and to get the submission done, I'm just going to be going over what I have now, and then adding that last few lines of code in and getting this all running and squared away. Alright, so the problem that we're going to be going over today involves this water bottle. Alright, now initially before we do anything to the water bottle, we are giving these initial conditions right here. So the initial pressure within this water bottle up here is at 1 atmosphere, or 101,325 pascals. Alright, and the initial temperature is 298 Kelvin. And the total mass of the liquid H2O down here plus the water vapor up here is 1 kilogram, right? So we are going to seal this water bottle. We're going to cap it off so that the system is closed, and we're going to add heat to it, all right? And we're going to add heat to it until the number of moles in the water vapor phase is going to be 0.3, and the pressure up here is going to be 2 bars or 200,000 pascals, all right? Now, we want to change this bottle so that the final temperature over here, we're going to want to solve for the final temperature and for the total volume of the bottle when these conditions are reached, all right? So since we have two unknowns over here, it's not going to be some simple sort of linear equation that we're going to be having to do. We are going to have to run a system of equations through Python, and it's going to get real complicated, so we are going to have to bring in this coding over here to do it, and we'll get to that part later. But first, we are going to need to come up with some equations that we're going to plug into our Python system that it can run through and solve, right? So the first thing we're going to want to do is we're going to come up with some easy equations that we know, and then we're going to work from there, all right? So we know one of the first things we can do right off the bat is we know that the total volume of this bottle here is going to be the volume of the liquid phase down here plus the volume of the vapor phase right here, right? That's easy enough. You know, the total volume is equal to this part plus this part up here, you know. It's just a fraction, all right? And from there, since we don't know what the volume of the liquid phase is going to be, we can bring in density to solve for that, all right? So the density of water is equal to the mass of the liquid water over the volume of the liquid, right? And we can multiply the volume over and divide the mass of the water by the density, and that will give us the volume of the liquid phase, all right? Now we don't know the mass of the water in the liquid phase, so we're going to have to bring in another equation to solve for the mass of the water in the liquid phase. And to do that, since we know the total mass of the water in the system, right? We are given that it is 1 kilogram down here. We can say that the mass of the water total is equal to the mass of the water in the liquid phase plus the mass of the water in the vapor phase, right? So we can simply track the total mass by the mass of water in the vapor phase to get the mass of water in the liquid phase. And then we can solve for that, and then we can solve for the total volume over here, which is one of the equations we're looking to solve for, right? Alright, so the volume of the liquid phase equation that we're going to be plugging into our total volume equation is going to end up being the mass of the water total minus the mass of the water in the vapor over the density of water, right? So we don't know the mass of the water in the liquid phase, so we're simply going to subtract the total mass from the mass of the water in the vapor phase, since we will know the mass of water in the vapor phase, right? Now we also don't know the volume of the vapor phase right here, so we are going to be using a ideal gas law. We are assuming that the air and the water vapor up here are ideal gases and they're not going to see each other. So we are going to do a PV equals nRT equation. And to solve for the volume in the vapor phase, we're simply going to do some algebra and divide both sides by the pressure to arrive at the volume of the vapor phase over here, and we are going to be able to plug that back into this equation. Alright, and another simple easy equation that we know is going to be true for this bottle is we know that the total pressure up here of the system is going to be equal to the partial pressures of the water vapor right here and the partial pressure of the air right here, alright? So the total pressure is simply just going to be equal to the pressure of the air plus the pressure of the vapor, right? Simple enough. But we are going to need to solve for the pressure in the water vapor and the pressure of the air since we are not given those, so we are going to have to go through and solve that. And to do that, we're simply going to do some more ideal gas laws over here, alright? So we have the PV equals nRT, and we're simply going to divide both sides by the volume of the vapor, so we can find this pressure of the water vapor right here. So we can plug this back into that equation, right? Alright, and since we don't know the moles of the air right here, we are going to have to shift this over to be able to solve for that. And right here we don't know the pressure of the air, so we're simply going to be able to subtract the initial pressure by the initial pressure of the water vapor, because since the system is closed, there's not going to be any air coming in or any air going out. So we can calculate the partial pressure of the air at the start, because it's going to be the same exact thing at the end, right? There's going to be an equal amount of pressure added from the air both at the start and the finish, since there's no new air molecules getting added. We cannot do that for the water vapor, because as it's getting heated, more molecules are coming from the water and going out and becoming gas molecules, since the heat is causing it to evaporate more. So we are going to have to calculate the water vapor at the final temperature over here. We will not be able to use it at the starting temperature. So when we're calculating the partial pressure of the air and the moles of the air over here, we are going to have to be using the initial temperature. Alright, and let's see here. So yeah, we are going to have to subtract the initial pressure from the initial pressure of the water vapor, since we do not know the pressure of the air when trying to solve for the molecules of air. And over here we are going to be having, since we don't know the volume of the air, we are going to be have to subtracting the total volume of the air minus the volume of the water vapor. I mean, not the water vapor, the water as a whole, which is the mass of water total divided by the density of water. That will give us the volume taken up by the water as a whole. And any space that's not being taken up in the water by the water within the bottle is going to be taken up by the air. So that's what that is saying right there. Alright, so now we have all of the equations that we're going to be plugging in over here. And alright, so what we're going to be doing later on in our coding is we are going to be bringing in a root function, as you can see right here. And what that root function is going to do is we are going to give it a couple of equations right here. We are going to be using the moles of the water vapor minus the moles of the water vapor desired is equal to 0. And we're going to be using the final pressure minus the final pressure desired is equal to 0. Alright, and we're going to put all these equations into the code, and basically what it's going to be doing is it's going to be trying to bring these equations equal to 0, right? So you're probably wondering, we have the final temperature and the total volume within our equations right here, and you're probably wondering, how can we solve these equations if we have unknowns in them? And basically what it's going to be doing is we are going to be setting the parameters right here. We're going to be putting in 200,000 pascals for the pressure and 0.3 moles for the water vapor. And basically what our code is going to be trying to do is we are going to put in an initial guess for these values right here, and it is going to run through, and it's going to try and get these equations equal to 0, and it's going to be changing the values of the final temperature and the total volume, and it's going to be bringing those up and down until it finds one that makes these equations equal to 0. And when these equations are equal to 0, we're going to know all of this is balanced out and the system is working the way that it should be. And yeah, that is going to be how our programming is going to work. We could change these parameters if we wanted to. Say we wanted to heat this up to 250,000 pascals and 0.5 moles of water vapor. We could simply change the values of the water vapor desired and the final pressure desired, and it would give us different total volume and final temperature calculations for that. So basically what we're going to be doing is figuring out a setup to where we can calculate the final temperature and the total volume for any given desired number of water vapor moles and final pressure that we would want in the future, all right? So we don't have to keep writing the code if we want to change the parameters or at all. We can just simply go in and change the values we give these numbers right here. Alright, so we are going to go ahead and hop on into this Python code, and I'm going to be going over what this system is going to be doing. So the first thing we did here is we imported this handy dandy repository that we're going to be using a couple times throughout our code. And basically what this is going to do is it's going to simplify a lot of our calculations. We're going to be using it for two different things. The first thing is any time we wanted to calculate the vapor pressure of something, we are going to be using it so we don't have to do the calculations ourselves, right? We can just say we want the vapor pressure at a given temperature. We can just use the system and then put in the temperature we want to find at that specific temperature we want to find the vapor pressure at. So for this one, we wanted to find the vapor pressure at the initial temperature, and so we just import this. And another thing is whenever we're doing a density calculation for a given temperature, we're going to be using this row hall function, and we're going to be importing the specific temperature we want to find the density, right? Because the vapor pressure and the density of water do change based on the temperature, if it's up or down. And we're going to want to account for that in our equation, so we're going to be using this. So basically how we do that is we use the git clone command, and we copy the link of the repository over here, and then we're going to want to change the path that it looks for so that it's nice and efficient and running smoothly and knows exactly where to go. So we use this syspath command and tell the code where to look. Alright, and then we import our tools so that we don't have to keep writing tools.che every time we want to use this. So we import it as che, and then right here we import our root command that we're going to be using later to solve this function. And then right here we use the repository, we use this p equals che props water right here to tell it that anytime we're going to be using this command, we want it to solve for the vapor pressure and the density of water specifically. There are many different compounds in this repository that we could account for, like isopropyl and so many other compounds, but we are just focusing water specifically since water is the only thing in this bottle that we're going to need to calculate for. So we want to make sure it knows that we're wanting to solve for the vapor pressure and density of the water right here. Alright, and then right here we are pretty much just putting in all of our conditions right here that we had. We have our initial conditions and our desired final pressure in moles of water right here. You can see that we're putting in our desired moles of water and final pressure, which we are going to be using down here. And then we also put in this R value, since R is a constant that we're going to be using in the ideal gas laws. Down here, as you can see, we're going to want to make that in so we don't have to keep typing it out. So we put that in right there. Alright, and now we are basically going to define this function, right? And we're going to call it vector, or just vec, and we're going to set the two unknowns that we're looking for equal to it so that it will solve for those. Alright, so we have the final temperature and the total volume equal to that, since those are the two things we're wanting to solve for, right? And now we're basically just going to put in our equations right here. As you can see here, we have the moles of air being solved for right here, and over here we solve for the total volume. We did have to work this in reverse so that we could find the moles of, or the mass of the water in the liquid and the volume of the liquid first before we could solve for this. So we did have to work this in reverse. And over here we are solving for the pressure of the air right here. As you can see, we have the ideal gas law for that. Alright, so basically the only two equations we have left to calculate is we have to put in an equation to solve for this PF value over here and the moles of water vapor right here. That's all we have left to do, and then we'll be able to get this running and we'll be able to solve for it, right? So the first thing we're going to want to do is we have the PF desired up here, right? We have our parameter, but now we're going to actually want to solve for the final pressure so that it knows how to change the equation to try and get the PF to equal the PF desired. So we're going to have to put an equation in for that, alright? Alright, so the equation we're going to be using to find this final pressure over here is simply going to be the pressure of the air plus the pressure of the water, alright? So we're going to go PF is equal to PA plus P water vapor, alright? And we already know the PA, we calculated it right here, so we're not going to have to do anything for that, but we don't know the pressure of the water vapor, so we're going to be using our PVAP calculation right here that we got from the repository. So we are going to go, hopefully we can reconnect here, there we go. We're going to go P.PVAP, and we are going to go with the final temperature this time, because we are calculating the final pressure over here. Alright, and then to calculate the, excuse me, we're going to be calculating the moles of water vapor right here, and to get that one, we're going to be doing an ideal gas right here. Alright, so let's look up the ideal gas law right here, make sure we got it down. Don't want to screw anything up this late in the game, alright? So we're going to be solving for the moles, so we're going to be dividing both sides by RT so we can isolate the N on one side. Alright, so we're going to be doing the volume of the vapor phase times the pressure of the water vapor phase, and since we don't know the pressure of the water vapor phase, we're again going to be using this PVAP calculation from the repository right here, so we're going to be doing the same thing, PVAP of the final temperature right here. Alright, and then we're going to be dividing that all by R times the final temperature, I believe, yep, times TF, like so. Alright, and we'll get some parentheses around all this just to be safe. Alright, and now this should all be good and ready to run. So we're going to go through, we're going to shift enter everything, make sure everything's running right. Alright, and then we are going to solve our root. Alright, so basically what this is going to be doing again is it's going to be changing the final temperature and the total volume until it can get the PF and the MWV to equal the standards that we set up here. So it's going to be shifting these values right here up and down until it can find values for both of them that make these equal to 0. That's what the root function does, alright? So we're going to be shift entering this and shift entering this, and hopefully you'll get it to run. Alright, so it is saying TI is not defined. Let's see here, alright, didn't want to make that capitalized, I don't think, so we'll go ahead and make that lowercase. Alright, so the iteration is not making good progress, so it looks like we did make a mistake somewhere in here. Alright, so we're going to be taking a little break, and I'll get back to you when I can get this sorted out. Okay, so I did manage to find where the mistake in the code was. We were using the initial temperature to solve for the density of the water, but we wanted to be using the final temperature. So we have TF in there now instead of the TI, and we got it running again. We'll just run it one more time just to make sure. Alright, and it is saying the solution is converged. Alright, so these are going to be our final answers right here. So it looks like the final temperature, our answer is going to be 373 Kelvin. and it looks like our answer for the total volume is 0.01 meters cubed. So that is going to be our final answers for the problem right here. And yeah, those are the answers for when you want the moles of the water vapor to be 0.3 and the final pressure to be 200,000 pascals. Again, let me know if you want me to redo the video. It will be a little while. I'm perfectly fine with whatever grade I get for this video. I know that even if I did finish it last night, it would have been a day late. But yeah, I just wanted to get this video out so it's not being waited on or anything like that. So yeah, have a good one.